So let's compute in this video derivatives of inverse trig functions. So this is a special type of inverse function. And we're going to recall that what is the sine of theta? Let's take a look at inverse trig functions by looking at just the sine function to start. So we can have a triangle, and we know that the sine of an angle is actually measuring the hypotenuse. Like if I'll have this, I'll label this angle as theta. Sine measures the ratio of the opposite side over the hypotenuse. So if I label the opposite side of the triangle as having height x, and the hypotenuse is 1, like if this were a unit circle, sine is the height of this triangle, then the sine is going to be opposite over hypotenuse, or in this case, just x. So what is an inverse sine function then? So I'll say sine inverse of x, which is also sometimes called arcsine. That's just this particular inverse trig function of x. This is saying that instead of plugging in my angle theta and getting out an x, I'm plugging in the height x into the inverse function, and I should get out the angle theta. So it's just undoing what the sine function does. And now we're going to talk about what is the derivative of this function. So I want to know what is the derivative of the inverse sine function, sine inverse of x. Well, we've already talked about a formula for this, that the derivative of this function is going to be 1 over the derivative of the inverse of this function, so the derivative of sine, d dx of sine, of this value of this function of the inverse function. So sine inverse of x. This seems a little messy, right? Because our g function in this case is my inverse function, so this is my g of v essentially on the inside. And the outside is the derivative of the original function f, and the original function f is just the sine function, because this is the inverse function, this is the original function. And we know a little bit about this. Some of these pieces are going to be easy. What is the derivative of our sine function? That's something that we know, right? It's going to be 1 over the derivative of sine is cosine. And then there's one little piece. Well, what is the sine inverse of x? This is asking, I plug x into my inverse function, and what do I get out? I get out theta, right? So this is actually just 1 over the cosine of theta. Someone might want to stop there, but the problem is that this notation, 1 over the cosine of theta, this notation isn't going to work because theta is in a different world than our x world. But I started by plugging in x into my function, and I'm taking the derivative with respect to x. This variable doesn't match this variable, right? That the cosine of this angle theta isn't the same thing as in my x land. So I need to be able to rewrite the cosine of theta in terms of x's. Thankfully, it's not hard to rewrite the cosine of theta in terms of x's because I have this triangle and I know my definition of cosine. That cosine, in this case, is going to be the length of this bottom side. And what is the length of this side? I can use Pythagorean theorem. I know that if my hypotenuse is 1, that means that 1 squared minus this side squared, square rooted, is going to be the length of this side, because this side squared plus this side squared equals 1 squared. That's the same thing as saying 1 squared minus this side squared is going to be equal to this. And what does that give me? That's the same thing as the square root of 1 minus x squared. So that means that the cosine of theta is going to be adjacent over hypotenuse, which in this case is 1 over the square root of 1 minus x squared. And we're done. We've converted our derivative of our sine inverse function back into the realm of x's. And next, I'm going to give you a table. You can verify individually on your own all of the remaining ones, or you can take my word for it that we just derived that the sine inverse is 1 over the square root of 1 minus x squared. Using the triangle in the exact same way, you end up with almost exactly the same identity here. The reason why this is negative is because the derivative with cosine is negative sine, and that's where that negative comes from. And all of the other identities follow from similar properties as well. But instead of deriving these, I want to conclude by doing one example. So for example, let's say that we have a messy derivative. We want to know, here I'll leave this up maybe for reference. I want to know what is the derivative of my sine inverse function that has a function on the inside. Notice that this is a great example of chain rule because I have an outside function and I also have an inside function. So what's the derivative of my outside function? The derivative of my outside function is the derivative of the inverse sine function, which I know is going to be 1 over the square root of 1 minus, not x squared in this case, but x squared plus 2 plugged in to the function x squared. So this is x squared plus 2 plugged into my function, right? Because the derivative of the outside function, this whole piece stands in for x, times the derivative of the inside function. What's the derivative of x squared plus 2? It's 2x plus 0. The derivative of the 2 is a constant. So I can simplify this and write this as 2x divided by the square root of 1 minus, I'm going to keep it as x squared plus 2 squared. I want to caution you, this is my caution, that you can't cancel the square root and the squared. No canceling. It's very tempting to want to take the square root of this squared term, but you can't do that because it's 1 minus this term. You would have to take the square root of this whole entire thing, which isn't something that's algebraically possible. So don't cancel, leave it as it is.